Let me introduce Mark Hebbel. He is the head of new business development for Basler. Mark got his PhD in particle physics from the University of Bristol. And as particle physics physicists do, he went to work for CERN in the Large Hadron Collider. And he collided a lot, and so he came to industry, and he has led a number of projects at Basler, and now he heads the new business development. So we're very lucky to have him. He's going to be talking about time-of-flight sensors. So please welcome Mark.
Thank you. I'm very pleased to be able to come here and present work that the Basler AG themselves did over the last few years we chose a sensor and integrated it, and I wanted to share some of the information, some of the experiences we had with that in this talk. I'll just start. I'm allowed to do one transparency to tell you who we are. We're actually a company who makes a large different number of cameras, just cameras which produce pictures, images in the memory for the customers, especially in machine vision areas and also in medical areas. As you can see, we have a large portfolio of different cameras of different types, different back ends, different front ends. What you won't see in this picture, because the camera didn't make it to the photo shoot, is our 3D TOF time-of-flight camera. And that's what this presentation is about. But 4 years ago, we didn't have any 3D cameras, and we were thinking about doing a 3D camera. And one of the first things we did is we got a Kinect and had a look at it. I remember this quite clearly. I took it home, wired it up to the TV, and then started playing around with it. And then for the first time, my son, who was 10, got really interested in what I was doing at work with a Kinect camera there. And we used it and we looked at this 3D stuff. And I think this is important because everybody wants to communicate with computers and stuff in 3D. That we live in a 3D world. We want to react in this dimension as well. And this is, for me, why 3D is important. Everybody can understand the world is not flat. So all of these cameras produce flat images. And what we want to do is produce a camera that wasn't flat. Now, we went through the same process, which Chris Osterwood explained this morning about how do I choose which kind of 3D camera do I want to use. And we said, well, we're going to look at stereoscopic, we're going to look at LiDAR, we're going to look at all of these stuff. And we came out at the end, for our market and what we wanted to do, we came up with a TOF camera was necessary. And so we went about to design a TOF camera. This talk is for absolute beginners. Okay, there's not going to be anything complicated. There's going to be some physics. There's going to be some tricks to avoid, some things to do, lists and lists of sensors and data for you to look at afterwards. But I'm not going to be able to describe 4 years' work from 10 people in about 40 minutes. So this is a very, very rough overview from what happened. So I'm going to start off with an extremely basic what is TOF, with pictures from Wikipedia, as you do these days. Then I'm going to talk about remember how fast the speed of light is and why this is relevant to building a TOF camera. Synchronization, lighting, shutter effects, everything you have to pay attention to when you want to build a camera with a TOF sensor. Or I always say camera, but anything with a TOF sensor, this is relevant. I'm going to detail which sensors are commonly available. In the case of TOF sensors, this is a very new technology. Some of the sensors are very difficult to get hold of. Some of the information of the sensors is very difficult to get hold of. Some of them are still very secretive. More about that later. And then at the end of it, I hope you realize this is a lot of hard work to integrate these sensors, and you may want to have a look at people who have already done this, and then maybe think about just buying the whole work already done in the form of a TOF module. And I'll talk briefly about that. And then when you're really, really excited about TOF sensors or modules or cameras, there's a few things you have to be careful about when you use more than one of them in the same room at the same time. And we'll come to that at the end. So, starting at the beginning. This is a bit of a overlap with Chris's talk to bring you into the right area of his talk. Why 3D? Well, we want to obviously analyze volume, measure volume. Some stuff is not very high, has no structure on it. If you have no structure on a tablecloth, a white tablecloth, a stereoscopic camera looking at it will have a big difficulty telling you how far away the tablecloth is. Or bad contrast in the pictures. So that the right-hand image, it's impossible to tell which one's not properly filled. On the left-hand image, it's pretty trivial to tell which one's properly filled. Any kinds of low contrast images can be enhanced if the depth information can be read out of them. So what we did was we looked at various markets which could use a TOF camera as opposed to any of the other forms of camera. So robots picking up packages, of course, sushi inspection systems, robot assembly plants, everything where it's important to know how far away something is before the grabber grabs it, and really up to the last moment and quickly. A rather nice use case, because I used to work on a machine that actually did this, cutting up fish. If you want to make fish fingers from a big piece of fish, you put the fish in, you have to measure it as quickly as possible, how big it is, how long, how wide, and then design where you want to cut out the fish fingers in the fish. And you can do this with several cameras pointed on the top and pointed at the side, and then trying to stitch together a 3D picture of the fish. But it's much easier if you just have a TOF camera at the top measuring how thick the fish is and measuring how wide the fish is. Again, in the middle, there's another form of picking up stuff with a robot, knowing about how far away it is. And obviously, steering stuff like this forklift truck on the right here. Being able to position stuff accurately to within a centimeter in order to pick up objects or to avoid hitting the person who seems to have just, the picture looks like he's just been injured. They obviously didn't have our TOF sensor in there. So I think Chris went in this morning to a lot of detail of all the different forms and advantages and disadvantages. In the reference slides at the end of my presentation, which will be available after the summit, I've put a big table in as well from our point of view what the differences are between the 3D technologies. But to concentrate at the beginning on the advantages and disadvantages of TOF, on the plus side, a large field of view, low processing power, fast integration, ease of use, everything is relative. It's difficult to get to deal with 3D data normally anyway, but it's fairly easy to integrate the one TOF module. No contrast requirements, like I said, it reads the information using its own light source. One component only, so instead of, if you have a TOF camera that can take a real picture, sort of a classic 2D picture with colors, and 3D information as well, you only have one camera, not two cameras. No moving parts. This is in reference to laser scanning. Laser scanning with a moving laser, of course, has mechanical parts and can wear out. TOF doesn't. Compact and high speed. The major problem with all time-of-flight cameras is ambient light, especially specifically sunlight. There are various methods to try and reduce the interference from sunlight, but all TOF cameras work much, much better indoors than they do, if they do at all, out of doors. And this comes from the large amount of infrared light that comes from the sun, which is very noisy and destroys any kind of TOF. Why, we'll see later on. Is the most important disadvantage to TOF. Multipath and scattered light, this is a similar thing because it's so dependent on its own light source. If anything else produces this light source, it will get confused. And this is the thing about multipath or scattered light. More about that later. And the depth accuracy is 1 centimeter, good or bad, depending on what you're comparing it to. But of course, if you use a laser, and read out a laser line with a normal camera, you can get a much better than 1 centimeter depth. But you have the simplicity of the one TOF module. So, assuming you have built a TOF system, what's actually happening? And what you're actually doing is you're sending out a light wave, obviously at the speed of light. From your lighting, it bounces off an object, like the blue line, the orange line, or the light blue line, and reflects into the camera. Now, basic physics is, if you know how fast light moves, and you know how long it takes to get from your light to the object and back again, you can figure out how far away the object is, because you know the speed of light and you know the time it took to bounce back. Actually quite straightforward. At this level, it all makes sense and it's very easy. One point at the bottom here, if you look for TOF cameras even in Google, you will get lots and lots of hits about single pixel TOF cameras, or 3 pixel or 12 pixels, all of these small numbers of pixels. These are very basic sensors just to measure distance in one dimension. They work on the same principle and they have the same effect, but this is a vision summit, so I'm going to assume you're going to be using a few more pixels than 2 or 3 pixels. Just to warn you in case you start Googling about this afterwards. Always check how many pixels are in the module. So, if we're sending out this ray of light, infrared light, into the world, and it's bouncing off something that's coming back again, it's coming back again as it says here, incoming pulsed light. Pulse, we'll see why in a minute. It hits some photosensitive element, it will be a pixel in the case of a sensor, and then through a switch mechanism, we can measure how many pulses or how many electrons come in, and effectively then how many photons come in from the light, and measure it in bins. If we assume we send out a pulsed light, the reason why we send out a pulsed light is for several reasons. One, so that we have an identifiable source of light, so we try and reduce the amount of noise coming from the sun and other lighting sources. Everything emits infrared light. But also because we need to measure the distance of the pulse, because we're going to have to integrate it later on. So TP is the distance of the pulse. The light travels outwards, reflects off a wall or something, comes back again, and it's moved when it comes back again, obviously, at time TD. So the x-axis here is time, and what we have is we have a pulsed light going out and a pulsed light coming back, and the movement in the light tells you how long it's been traveling by. So if you build in a shutter, or 2 shutters like we have in the diagram, then you can integrate, you can count the light pulses which come back, or the photons which come back reflected off the wall. And you put this into 2 shutters which are separated, so you always integrate how much in this time span, how much in this time span. By some very simple mathematics with the amount of light that lands in S1, the second one over the total amount that you've measured, to normalize it, multiplied by the speed of light and the time traveled, you effectively get the distance, how far it's gone. TOF cameras basically work on this very, very simple principle. What, of course, very exciting is how to get all of it to work together. So you have to generate the light that goes out into the world and measure it when it comes back. You can have 2 different kinds of pulsed light, either square wave modulation or sine wave modulation, which are both shown here. Both have their advantages and disadvantages, and they're just 2 different ways you can do it at the moment. For anybody who has knows that light itself is a wave, this is the pulsed, this is not the wave of light, this is the pulsed light going through the system, or being reflected from the wall. So let's start with the sine waves, sinusoidal waves. They have an advantage that they work with cheap old LED technology. So You can get any old infrared LED into your system. You can send out this sinusoidal wave, pulse light, and things work. The disadvantage is sinusoidal waves are exactly what you find in nature. The sun produces a lot of them, so you get very confused by sunlight. And you require a special pixel design in order to integrate it properly. It can result in larger pixels and lower resolutions in the spatial x and epsilon directions, x and y directions. So the more popular way these days is to use a square wave pulse light. It's more accuracy because you have a better defined start of pulse and end of pulse. It's quite clearly at these sharp edges you can measure the time much better than you can at a smooth edge from a sinusoidal wave. With the right LED optics you can have much larger opening angles, so you can see a much wider field of view than you would do with a sinusoidal wave. And you can have smaller pixels due to the way the sensor is built on the silicon. The major disadvantage to this new to the square wave is you need special LED technology. These are VC cell diodes, which are more expensive, but you need them in order to produce this very hard edge, because old-fashioned diodes can't produce that. So this is the disadvantage to it. Depending on what you want to do, you have to then decide which technology you want to use. If you want to save more money and have a not so accurate design, or you want to spend more money and have a more accurate design. So, to integrate in the sensor. There are three kinds of sensor architecture. What I actually just described are the demodulation devices in the middle there, which are very popular at the moment. All the famous sensor, all the famous technology is based on demodulation devices, is what I just described. Electronic fast shutters are a way of doing stuff which is a bit older, where you open the pixel long enough to count the light and you close it again, and you don't demodulate with the two different shutters. You need much more electronics on the pixel, and of course when you start putting electronics on the pixel, you either have bigger pixels or less sensitivity on your pixels. So you affect it, because you can't deal with less sensitivity, you have a larger pixel size. You can also not put any amplification on the pixels, making it difficult to see very small signals. What's in research at the moment, and I mention all of these more so that you can Google them later and know what the difference is between them then from there, is single photon avalanche diodes, which are also based on particle physics instruments. They have a special way where they amplify the electron or the photon coming into many. So they're very, very sensitive. But because of the way they work in an avalanche method, like a snowball falling down a mountain, they have very low resolutions because they can only deal with large pixels at the moment. So the best compromise of technology at the moment is the demodulation devices. So if we concentrate on demodulation TOF sensors, there is no ideal sensor for everybody. Everybody has to choose their own one. And there's a series of criteria here depending on which market you're looking at, which product you want to build. You have to figure out what these mean to you and what their priority is. The first four I will just leave there. I mean, they're all classic ones from vision sensors. A normal sensor for a normal camera, a 2D camera, will know the first four. Low noise, high sensitivity, I think are pretty clear. What's interesting and different are the four last ones. You need a high quantum efficiency in the infrared. This is obviously because you're sending out infrared and receiving infrared. So you need to be sensitive to it. Normal sensors try and cut out the infrared. Normal vision sensors cut out the infrared because it ruins the quality of the 2D image. But you actually need this for a TOF sensor. You need a high demodulation contrast in order to be able to recognize the wave coming in. You need to be able to, of course, modulate very high, so you can actually get these pulses as high as possible. What I didn't say before is this time for a high pulse. The shorter you can get that, the more accuracy you can get in the Z direction. So you want to keep that as short as possible. In order to get as short as possible, you need a high modulation frequency. So that's a very important bit for your accuracy. On the other hand, before you all get too excited and say, oh, okay, I want a very, very short pulse height, you also have to be able to handle it with your electronics, which is also not so easy. And in this embedded circle of people, I don't have to say you also need low modulation power. I mean, you don't want to spend so much power just powering top sensors. Top sensors are anyway take a lot of power, and you want to try and reduce that at least with the modulation. So now we come to the sensors. The sensors are all based on absolute most modern technology. It is extremely difficult to get information on them. It's practically impossible to find in the web. And what I have found, I've put in the back of this presentation in the information slides at the end. You can reference it. It was accurate as of February this year. Normally, you have to get to know a sensor supplier for such sensors. You have to find out that the sensor supplier even sells TOF sensors in some cases. You have to sign an NDA, and then they'll start talking to you. Then you get the information. What this means is even for the sensor that we use in our cameras, I can't tell you that much about it because it's all under NDA. So it's all very secretive, which is good because they're all protecting their secrets. It's bad because they're not going to get much advertising from me here. This is the list which I managed to find from available open sources where I didn't go against any of the NDAs we signed. I got this checked by several people. There's some famous names on here. PMD is probably one of the most famous one. Panasonic is what we use in our cameras. There's available from TI, Melexis, SPROS at the end. Samsung I have listed. I found many blog articles about this Samsung chip, which the name is there in the second column. I could not find anything on the Samsung webpage about it. So I have no idea. It's not that old. The blog articles are not that old. So they must have had something there. And if you're interested in looking into these, you'll have to contact Samsung separately and get information. That's why there's so many question marks at the end there. As you can see, the resolutions are not what you expect from a 5 megapixel world or a 12 megapixel world, or my newest mobile phone has 13 megapixels. This surprises lots of people. These are, for a normal camera, very, very low resolutions. And before you design anything or think about what you want to do with them, you have to take these into account. They're getting better, we'll get to that at the end again, but they are very low resolutions compared to a 13 megapixel sensor that you can get for a few euros. The packaging is also very different. It can be adventurous. As far as I know, the PMD one from Infineon is only available in bare die. That means you have to really deal with the packaging. The others are packaged. The frame rates. I have no idea what Melexis means with 600 frames per second raw. Especially as all the other ones are by 45, 30, and 65. TI is a bit more honest and says in certain cases, I mean Melexis is also honest, but TI says in certain use cases, and lists a couple, then you can get up to 150 frames per second. When you can get a Melexis up to 600 frames per second raw, you have to try out and talk to Melexis about it. I don't know. It seems very strange that it sticks out so much. Power consumption, as I said, when it's available on the data sheets, is very high. I mean, these are quite, especially the SPROS, which is you could use to heat things with, is you will have to dissipate the heat somewhere when you do your system. Those are the hard specifications. So they're in the data sheets, which are at the end of the presentation, like I said. Now we come to some soft specifications. Jeff Beer wanted that I list the prices. The prices are definitely under NDA. So but I can say they're on this range. And then Jeff, we went backwards and forwards and discussed this presentation. He said, that can't be possible. They're thinking of building these things into mobile phone cameras. into mobile phones, and nobody pays $100 for a mobile phone sensor. And he said, put down what units you're talking about. When we asked and did this research, we were talking about volumes of up to 10,000 a year. Of course, if you're in the million units a year, you're in a completely different area. And I think you get different prices as well. But talk to your favorite sensor supplier about those. The other interesting question that comes up very often and is very difficult to answer is what is the maximum distance in Z that I can really measure? Not the accuracy, but the absolute distance. How far away am I allowed to bounce the light off? And again, the specifications from these companies vary from 9 meters up to 9 meters, which I can believe, to up to 240 meters in one of the data sheets where I'm thinking, okay, I need a use case here. What have you built to do 240 meters? I find it's very, very difficult to see the use case there. I mean, I can guess lots of things you could use before, but I don't know what they built together to test this 240 meters. So take all of these specifications with a pinch of salt and see what really works when you try out your prototype designs. As Jose said, I worked in a nuclear particle accelerator. I actually helped design, build a nuclear particle accelerator where we accelerated particle matter to near light velocity. Light is very, very fast, free with lots of zeros behind it. Electrical signals are very fast, not the electrons themselves, but the signals themselves. And that means the time it takes a signal to go around the track on a PCB is relevant. The length of your tracks on your PCB become relevant in this game because you're sending out a pulse beam of light which is reflecting at the speed of light, and even if it's 9 meters away, as I've written there, 1 meter is done in a very short part of a second, it's going to be back extremely quickly. And so you need to get the trigger in between your light pulse and your when you receive it completely correct, and the length of the track on the board is relevant for this. Also relevant, of course, is the temperature of the entire system. Copper changes length, the hotter it gets. Your track length in your PCB will change length. That means you will have a different result from your TOF sensor before you turn on the electronics, if that was possible, during the warm-up period, and at the end when it's fully warm. So especially for the sensor which produced 750 milliwatts, it's going to get warm, it's going to make everything expand, and you have to get this expansion out of your system. You have to calibrate it out, because you can't beat the laws of physics. You have to calibrate it out in order to measure the time correctly for the reflection. So, I've said this quite often, the PCB track length is important from all of these factors. You can't change laws of physics, so calibration is important. How do you calibrate? Quite easily, but of course you have to, if you're in an industrial area, you have to do this properly. You have to perhaps certify it, perhaps not certify it, depending where you are, what kind of customers you have, how accurate they want it. So this is the setup we use. A sheet of white paper against a checkboard. Positioning of the camera away from the piece of white paper to an accuracy of 0.1 millimeters. A fixed room temperature, which is held stable. Warm-up time for the entire electronics, because otherwise, as I said, the PCB length gets bigger, the tracks get bigger. No ambient light. I mean, you can see a bit of the black curtains there around the edge. You don't want to get any sunlight into your calibration, otherwise it's going to mess it up. Probably by 40 pixel white piece of paper and a checkboard there, and over several images. We use 25 images and then you average. It's important to average and get all the statistics right. What do you get at the end then? You then get the x-axis is the distance away from the camera, the z-axis, and you get a distance error on the z-axis. And in the case of this sensor with this setup, we get an error from about 1 centimeter over 6 meters. And so this is our sensor and our camera, so this is what we say. We have an accuracy of 1 centimeter, which is what we showed earlier on. For those of you who know about statistics, is if you have a Gaussian distribution of all your 25 image points. This is, of course, your mean, the center of your distribution, the average error. You also have the spread of your errors, the width of the Gaussian distribution. So how accurate, if you do 25 images or measurements at 6 meters, how much do they vary? This is your standard deviation. Firstly, in the x and y direction, so distance is still the distance away from the camera, and then you have the x and y spatial standard deviation. And you have then about 11 millimeters at the 6 meter mark. So on the 1 centimeter, you have then an extra centimeter, which is your width of your distribution. So, and the funny jump at the beginning by 1 centimeter is because of an HDR routine, which we take 2 images. Starts off with the 1 image and then goes off to the other image at that point because the error becomes too large. So that's an artifact of our system more than from the sensor. The same for temporal noise or the wobble in the Z accuracy of about 8 millimeters on 6 meters. Multipath effects. This is something you have to look out for when you do this stuff. It's also how relevant it is depends on your product and your market you're selling into. As you can see here, light reflects from different objects or part of objects and lands in the same point in the camera. This, of course, ruins the measurement of the distance at that point, and you have to somehow get that out. That's dependent on your. That's a problem that everybody has to solve in their own product. The same is true, of course, scattered light from completely different objects to reflected on the camera, which can also be reflected inside, in the case of a camera, but it can be any system with a TOF sensor in it, which can be then reflected into the camera sensor. As I said, the whole thing is extremely complicated. Especially getting calibration and everything. This is why several companies produce modules where the lighting and the sensor is already built in together in a nice little box that you can just plug in, the so-called TOF module. And I wanted to produce the same kind of table as before for the TOF sensors because I like to try and be systematic. It was very difficult. I couldn't find actually any parameters which you could compare between the producers of such modules. So I'll just, I forgot since just come up to the minute. Why use a TOF module? In the same way that nobody really integrates a processor anymore on a board, they integrate mostly an SOM in their system, so they can change the SOM when the newest SOMs come out. You can think of the same idea for a TOF module. You don't want to have to redesign the whole calibration and everything every time the new TOF sensor comes out. So why not just buy a module that already does it? Light integration and calibration. And then you have it all in a nice little box which you just plug in. And what I said before was I couldn't compare it. I mean, we have a sort of TOF module. It's a bit bigger than the other two, but you can look at these companies, you can see what they're making, and I wasn't able to quickly compare them. So I mean, you'll have to look at it yourselves with your own market analysis, see which one probably fits. Okay. So coming to the case of multiple TOF modules. As I said, you can get very excited and say, okay, we like TOF. We've just built a TOF camera. We've installed a TOF module. It's not just modules, but it happens quicker in modules. What happens when you have 2 of them? You can get, of course, interfering light from your own system. If you have 2 modules pointing at a wall, because you want to get double accuracy, the light from this will reflect off the wall into the other camera and confuse the other camera because it's only expecting light from itself and not from the second camera. In the worst case, when you decide you have a box going along here and you want to measure it from left and right for some reason because of indentations in the box or something, you're going to have two cameras pointing directly at each other. And they're going to see each other's light directly, and you have such problems. It sounds trivial, especially when I say this like this. It sounds quite funny probably, but it can happen very, very quickly if you don't be careful, because you just plug the cameras in. Perhaps you plug one in and you decide to put one on the other side, and suddenly the system doesn't work. So when you build these systems with more TOF sensors or modules, be careful that they're not looking at each other or interfere with each other. Otherwise, you'll get very interesting effects. Also, if you're taking pictures of the same object, you're going to have to synchronize them somehow over PTP or TNS. There's two possibilities. Build it into your system design from the beginning and not later on. What I have done here is taken a very physics point of view. I have seen presentations on TOF sensors which last entire days, or an entire day, about the electronics and the silicon of it. I haven't repeated it because I'm not an expert in silicon design. There's lots and lots of information available on the web, and I'm trying to summarize here in the next slide what are the important future trends that we should be seeing in the area. So what can you rely on will happen, and what's less likely to happen. I guess there's no surprise here. If I'd written anything other, everybody thought it was a bit weird. Everybody's pushing for smaller pixels and higher resolution. The sensors I showed you in the first transparency, at least one of those sensor producers have produced sensors which are higher resolution now, much higher resolution. Well, you're still not in the 5 megapixel area, but you're getting to the 1 megapixel area. More combined 2D and 3D imaging. Generally, TOF sensors, there's becoming more and more of them. That's the point of the sensors, is they're not unique. There's not just PMD Infineon doing it. There's a whole series of them now. And, of course, reduced power consumption for mobile applications. I think there could be some very, very interesting applications on mobile telephones when the TOF sensors have reduced power so they can be put on there. And I think this market is definitely, the mobile phone market is definitely pushing the sensor producers to produce lower and lower power consumption. The problem with the LEDs also has to be solved, but that would be a topic for another talk. So I'm pretty much in time, so I'll just finish off with a summary. TOF has a high-speed advantage because it has two sensors combined into one, a depth sensor and a normal image sensor. This allows higher speed because you can just take one picture in three-dimensional information and just use it, and not have to synchronize a real camera with a TOF camera, so to say. TOF is tricky to use. It's almost impossible to use outside in the sun in a beautiful day like we have today in California. But it's tricky to use even if you're near sunlight, near a window. We have customers who have problems. They open the curtains, so to say, of their windows near the TOF machines because the ambient light comes in. And of course, what I said, if you start using more TOF, several TOF cameras in the same area, try and make sure that they're isolated, otherwise they'll confuse each other. I think the main point of the talk is building a TOF camera or any sort of system with a TOF sensor in it is complicated due to the physics restrictions of the camera, of the technology, because of the high precision required. And I think everybody should be well aware it took us many, many years to get this right. And that's why I can only recommend buying a TOF module when it works for your case. But as it says, with all technology, it's improving rapidly, and we should expect big progress, especially in resolution. Power consumption, I'm hoping for as well, but I think the resolution problem they're getting to at the moment, because as I said, people expect such high resolution from the normal picture now. They don't understand when they see such a low resolution in a TOF camera. And that was that. And I think I talked too quickly because I still have lots of time left.
Thank you, Mark. This was really very interesting. Thank you very much. And you're right. When you Google TOF sensors, you just get 1 pixel or a few pixels. So thank you for bringing that information. And if I learned something today, is that tough is very tough.
Yeah.
So thank you. Questions?
So the last talk on 3D sensors mentioned that one possible way to reduce multipath would be to use polarization. Do you have any experience with doing that and how it affects it?
No, we haven't done that yet. I can't say. I can only imagine it improves it because you make the signal more unique. We also had a talk about introducing more frequency variations or some sort of coding in the pulse signal. That would also work in that direction as well. But the polarization is easier. If you modulate the signal more than just doing a square wave, you put some information into it that you can decode, then you have less effect from ambient light, for instance, would also be a possibility. But we haven't done that yet. So.
And do you have any advice on kind of like software filters or any such to try to reduce, deal with noise that you see or multipath issues or any of that sort of thing?
Yeah, I mean, you can. It's difficult. I mean, you can try and do some sort of edge finding outliers. If you find a dimension where there's a plane or something, you can try and get the outliers out of it. It's much harder. I saw a presentation at the summit with gesture detection where it's exactly this problem. How do you tell the edges from the hand and everything? That's a whole other series. We don't look at that really. That's too much research for us then. Okay.
Hi. Do these sensors suffer from specular issues when you're looking at shiny objects and such?
Yeah, because of the scatter light effect, you're going to get several light beams which reflect back into your camera in the same path.
Any solutions to separate the light source from the camera to be able to image specular surfaces in that case?
We haven't tried. The point is most of them are the light source is very close to the camera, otherwise you get more problems with the timing again. The farther away they are, the worse the timing problem.
All right, thank you.
Interesting talk. You mentioned that there aren't any imagers out there that can deal with the sun. Do you see that changing? Have you seen any smoke signals on the horizon that there may be tough imagers that can handle sunlight conditions?
And really, the problem is to identify the waves of light that you have sent out. So if you can encode them by polarization or by some kind of frequency modulation, you could do something like that. But the technology as it stands, the sun is producing a lot of infrared and all sorts of noise. So it's going to ruin every system.
Okay, thanks.
Okay.
Let's see, any other questions? I have a question. So you mentioned that briefly you mentioned about multipath reflections. But can you give us a hint of how to solve multipath reflections?
You have to try and do several frames and average the data somehow, but this was the question before about if you can get these outliers out of the system. But it's much more difficult in a two-dimensional system because then you have a three-dimensional grouping where you have to find the outliers in three-dimensional grouping. So you can imagine if you're supposed to see a wall and you see a few points here and there, then you can try and throw them out. But it depends on your application, it depends where you're using it. A general solution is not so easy. This is a very, very new area of imaging, that's why.
Also, you mentioned about PCB track length being important, especially under heating situations. So what is the tolerance that starts to get in the way? How many microns does the track need to vary?
I think I had on the presentation something like 1 Kelvin difference starts to become interesting.
1 Kelvin.
Yeah, I think so. Something like that. Of this level. At least 10 Kelvin you definitely have to calibrate out, which is a normal temperature change in a day. So.
Okay, any other questions? Well, thank you. This was fascinating. Thank you very much.
Thank you.